Hey, welcome to The Explainer. This is where we take really complex stuff and, well, we make it make sense. Today we're talking about trapping a lightning bolt.
You ever wonder about that? How a camera flash works? It's like a burst of artificial lightning right there on demand. It seems like magic, but it's not. It's physics. The secret is this remarkable little device that acts like a tiny, super-fast energy reservoir, designed to catch, store, and then release all that energy in the blink of an eye. And here it is. It's called a capacitor. It's one of the most fundamental, most important little parts in pretty much all modern electronics. But to really get how it traps that lightning, we first have to understand what it's made of. And really, it's a story of two very, very different kinds of materials.
Okay, so let's dive right in, starting with conductors. We're talking about things like metals. And these materials, they have what you could almost call an electrical superpower. It's what makes everything else we're about to talk about possible.
Now, the phrase you got to remember here is sea of electrons. Seriously, picture it. In a piece of metal, the atoms are kind of like islands, but the electrons are the water, just flowing freely all around them. They don't belong to any one atom. And this freedom, this ability to move anywhere, is what defines a conductor and gives it its incredible properties when an electric field shows up. So check this out, because this is where the magic happens. A conductor has this amazing self-defense mechanism. The moment an external electric field tries to push its way in, that sea of electrons just instantly rearranges itself. The negative charges flood to one side, leaving the positive bits behind, and bam! They create their own perfect counterfield. It's automatic, it's instantaneous,
and that is the superpower. The net result is that the electric field inside the conductor becomes zero. Gone. It doesn't matter how strong the field is outside. Inside, in a static situation, it's a completely field-free zone. This whole thing has a really cool name: electrostatic shielding.
So, the main takeaway here is that conductors create a perfect, safe space. If you put any extra charge on one, it just hangs out on the outer surface. The whole thing stays at one constant potential. They are, for all intents and purposes, the ultimate electrical shields. You got to remember that because it's absolutely key. But, conductors are only half of the story. To build our energy trap, we need their complete opposite: insulators, or as physicists like to call them, dielectrics. And they play a totally different, but just as critical role. Okay, so now think about stuff like rubber, or glass, or even pure water. In these materials, the electrons are not in a free-flowing sea. Nope, they are tightly bound to their own molecules, kind of like they're on a leash. So when you put a dielectric in an electric field, the electrons can't just up and run to the other side like they did in the conductor. Instead of all the charges running for the hills, something way more subtle happens. The electric field pulls on the charges inside each molecule, just stretching them out a little bit. This turns every single molecule into a tiny little magnet, what we call a dipole, with a positive end and a negative end. And then, all of these tiny molecular dipoles line up with the external field, and together, they create their own opposing field right inside the material. And this table just lays it out perfectly. A conductor's free charges move around until they completely cancel the external field inside. A dielectric's bound charges, on the other hand, can only stretch and align, which just reduces the external field. It weakens it, but it doesn't get rid of it. So you see the difference? One is a perfect shield, the other is a field weakener. All right, so now we have our two essential ingredients: the perfect shield, our conductor, and the field reducer, our dielectric. It's time to put them together and see exactly how a capacitor stores that spark. The design is actually beautiful in its simplicity. You just take two conductive plates and you stick a dielectric material right in between them. That's it. That is a capacitor. By putting that field-reducing insulator between two of our conductive shields, we create a device that is perfectly designed to hold and store electrical energy. So here's how it all comes together. You hook the capacitor up to a battery. Charge starts to flow, making one plate positive and the other negative. This, of course, creates an electric field between them. But now, that dielectric in the middle does its thing. It gets polarized and creates its own opposing field.
This opposing field reduces the overall electric field, which makes it easier for the battery to push even more charge onto the plates. So the dielectric is basically a booster, letting the capacitor store way more charge than it could otherwise. And this boost has a name. It's quantified by a number called the dielectric constant, which we just call K. A vacuum has a K of 1. Air is super close to that. But if you stick a material in there with a K of, say, 6, you can suddenly store 6 times more charge for the exact same voltage. The dielectric is basically a capacitance multiplier. It's a game changer. And you have no idea how essential this multiplier effect is. I mean, to give you some perspective, a standard unit for capacitance is called the farad. If you tried to build a 1 farad capacitor using just 2 metal plates separated by a centimeter of air, do you know how big those plates would have to be? They'd need an area of about 10 square kilometers. That is massive! But thanks to dielectrics, we can pack that same power into a little component that fits on your fingertip.
And as you can see from the physics here, the energy a capacitor stores is all about the charge and the voltage. By packing a huge amount of charge in there, a capacitor can hold a pretty significant amount of energy. And here is the crucial part. That stored energy can be released almost instantly. It's not a slow drain like a battery. It's a sudden, powerful discharge. And that's your camera flash.
So we've figured out how to trap a spark. But this isn't just about camera flashes. These fundamental principles, shielding and energy storage, are literally the building blocks of pretty much all modern technology. Think about it. That exact same principle that makes a conductor a perfect shield, that zero internal field, that's what we use to protect all of our sensitive electronics. The metal case around your computer or your phone is acting as a shield, protecting all those delicate little microchips inside from any stray electric fields out in the world. And it gets even cooler. By combining capacitors in different ways in a circuit, engineers can get incredibly precise. If you connect them in parallel, their capacitance just adds up. It's like adding more water tanks to store more energy. But if you connect them in series, the total capacitance actually goes down, which gives you this really fine-tuned control you need for things like timers or radio tuners. It really is amazing when you step back and think about it. From storing a tiny spark for a photograph to shielding the very brains of our computers, the simple physics of how charges behave in conductors and insulators, well, it powers our entire modern world. It all just comes down to controlling where charges can go and where they can't. Which really makes you wonder, doesn't it? What are we going to build next with that power?